Hello. So we're going to discuss chapter 7, section 4. It's about integrating irrational functions by the partial fraction decomposition method. So we already went through this. We went through case 1. So we did case 1 where Q of x was a product of linear distinct factors, and then we also did case 2 on our two previous videos. So we did case 2 where Q of x was a product of this distinct linear factors where some of those factors are repeated, and now we're going to discuss case 3. So case 3 is different from case 1 and case 2. So case 3, here Q of x is a product of distinct irreducible quadratic factors. X squared plus s squared is called a quadratic factor. It's irreducible because if you set, for example, here's an example, x squared plus 4, s squared is 4. Now if you try to you set this equal to 0 and then try to solve this equation for x, you will only get the complex solutions or imaginary solutions. You will never get the real solutions. So those quadratic are irreducible on the set of the real numbers. So this is case 3. Now, what is then the partial fraction decomposition in this case? So we're still dealing with the integration of a p of x over q of x dx, where a q of x is a quantity x squared plus a squared times quantity x squared plus b squared. So let's start with the partial fraction decomposition. So we have a p of x over x squared plus a squared times x squared plus b squared. To do partial fraction decomposition, we will take this quadratic factor, x squared plus a squared, as a denominator. Now watch the numerator. So the numerator is you decompose this quadratic factor as ax plus b. So a times x plus b. Plus, then you go to the second quadratic irreducible factor, x squared plus b squared as a denominator, and then you continue with your alphabet, cx plus d. So this is how you decompose a rational function where when q of x is in irreducible quadratic factors. So it's totally different from what we did in case 1 and case 2. But we want to just discuss one of those in terms of integration. So when we integrate ax plus b over x squared plus a squared dx, first we're going to split this into two terms. You have ax over x squared plus a squared, and then plus b over x squared plus a squared. The integral of a sum is sum of integrals. So we're going to integrate each term and then add. So we integrate this plus the integral of the other. The integration of this is, since a is a constant, we can move it outside of the integral sign and then integrate x over x squared plus a squared dx, which basically this we can solve it by the u substitution. If you let u be x squared plus a squared, then du is a 2x dx. Since you have x dx, you can then solve for x dx by dividing this equation by 2. And then it just becomes a substitution problem. You get 1 over u times 1 over u du over 2. And then you bring 1/2 outside, and then to integrate 1 over u, we know it's just a natural log of absolute value of u. And when you go replace u by x squared plus a squared, then you're done. For the for the second integral, when you ask to integrate 1 over x squared plus a squared, we know this is this is case 2 of the trigonometric substitution. So trigonometric substitution where you have to set x equals a tangent theta. So when you plug this in, you're eventually going to get so your final answer is going to be 1 over a times arctangent of x over a plus a constant of integration. So you don't need to know, all you need to do is when you see this, then the answer is that. Okay, you don't need to do it again using the trigonometric substitution. Case 2. So let's take an example. You are asked to evaluate the integral of 1 over quantity x plus 5 times quantity x squared plus 90x. So here we have a mixed case problem. X plus 5 basically tells us we're going to use case 1. X squared plus 9 tells us we're going to use case 3. So we go by partial fraction decomposition. So we can decompose this as a over x plus 5, which is case 1. And then plus, since this is case 3, then we continue for the alphabet. We get bx plus c over x squared plus 9. So to find a, b, and c, what we're going to do is clear this, clear all fractions. Again, for all cases, to clear all fractions, we will always multiply by q of x, by this denominator. So we'll multiply the equation by the denominator, both left and right. So multiply by quantity x plus 5 times quantity x squared plus 9. And then here, because we have addition, so we're going to multiply each one of them by the same factor, the same q of x. So on this side, we eliminate, we simplify, we get 1 left. And then here, we can simplify x plus 5 to get a times quantity x squared plus 9. And then over here we can simplify x squared plus 9 to end up with quantity bx plus c times quantity x plus 5. So from here we can expand everything. Here we can distribute a, and then over here we can FOIL it, give us this. And then from here we're going to collect like terms in terms of x. So we have x squared. This is x squared term, and that's x squared term. So we can add them by factoring out x squared. So you have quantity a plus b times x squared. Then we go to x. We have 2 terms of x. So we can factor out x. We end up with quantity 5b plus c times x. And the constant terms are the terms that do not have x. We have 9a and 5b. So we get 9a plus 5c. But so we're comparing at the right side with the left side. So we're comparing 2 polynomials. Here we have only 1. So we can, since on the left side we have x squared and x, we can make 1 to be a polynomial of degree 2 by taking 0 times x squared plus 0 times x plus 1. Because if you take 0 times x, it gives you 0, plus 0 times x squared is 0. So you have 0 plus 1 is still 1. We did not change it. We just want to show x squared and x. So when we compare, we're comparing coefficients. We're comparing right side, left side with right side. But we look for the x squared terms first. This is x squared terms, and so is that. So when you compare the 2 terms, you're going to compare coefficients of x squared. So you get the coefficient of x squared here is 0. The coefficient of x squared there is a plus b. So that generated this equation a plus b equals 0. We call that equation 1. And then we go to x term. We compare 0. We set 0 equals 5b plus c. We can rewrite it as a 5b plus equals 0. So that's equation 2. For the constant term, we will have 1 equals 9a plus 5c. And we can rewrite it as 9a plus 5c equals 1. So we want to use this method, the matrix method, to find the a, b, c. So we will write equation 1. So equation 1 is a plus b equals 0. So we write it here. Equation 2 is 5b plus c equals 0, which is that. Equation 3 is 9a plus 5c equals 1, so which is this one. So now, how do we write it? We have to have a four columns. We have one A columns. So here is column with A, and then the second one is column with B, and then a C column, and then we have equal sign, and then we have the constants. So we have to set it up this way, so that when we create what we call the augmented matrix, we will only take the coefficient of those A, B, and C. For example, on column 1, we have A has 1 in front of it, so write 1. Here there's no A, it means the coefficient 0. And the last one we have 9A, so the coefficient of A is 9. So we create these A columns. B column is the same, 1, 5, 0, so 1, 5, 0. C column, since C is not here, we have a 0, 1, 5, 0, 1, 5. And then we have equal sign is represented by this vertical bar, and then a 0, 1, 0 is the constant. So this is what we call augmented matrix. We're going to take this matrix, we're going to enter it on your calculator. You can have a TID 3, TID 4, TID 4 plus, and then you enter it, and you look for under matrix, you will see this function RREF. So you're going to RREF your matrix. When you RREF your matrix, you press enter, it's going to generate this matrix. Now this matrix gives you the solution. This matrix here, what you see here with the 1 on diagonal, we call this identity matrix of a 3 by 3 matrix. The solutions A, B, C are given here on the last column. So it depends how you set it up. So if this is A, B, C, you set it up this way, then your first answer is going to be A, the second one B, and then the last one C. So we get our constant. A is 1 over 34, B is negative 1 over 34, and then C is 5 over 34. So we go back to the partial fraction decomposition, we plug in A, B, and the C, and we get our partial fractions, decomposition of this rational function. So now we go to integration. So to integrate the original integral means we're going to integrate these three partial fractions. Now the first one, we will move 1 over 34 outside, then it just becomes the integral of 1 over x plus 5, which is natural log of absolute value of x plus 5. The second one is after we move 1 over 34 outside, we get the integral of x over x squared plus 9 dx. This just begs us to use the u substitution. U is x squared plus 9. So if you let u to be x squared plus 9, then du is 2x dx, so du over 2 is x dx. So we kind of did this. So when you plug in the u, you get 1 over u du over 2. Bring 1 over 2 outside, then you only end up with the integral of 1 over u, which is natural log of absolute value of u. And then you go here, you replace u by x squared plus 9. And then you're done. The last integral, after bringing 5 over 34 outside, we have this integral of 1 over x squared plus 9, which is basically, is going to be arctangent. Okay, so a is 3, so it's going to be 1 over 3 times arctangent of x over 3, which is that. So basically that's case 3, and then we're done for now. Thank you.